But it's like if I add more things, it's gonna like now that you're like like me, I've been to the drink out.
I didn't do much.
It's gonna be just my line.
I still know my driving so well. Yeah. Oh my God, I need to so close. It's one year.
I didn't say I got you back.
I didn't it's like, oh, yeah, that's how it is. That's how all these are. Yeah, that makes sense. I think like 20 stuff. I mean, like, well, you like, you know, you're like, something. I buy it. Like, well, you know, yeah.
Okay, guys, let me go over the calendar here, just to give you an idea what this week looks like. So we did Euler's method over the Teams lesson virtually on Friday. And this will be what you'll be working on tonight or for tonight's homework to show for tomorrow. Today, we're going to be going over logistic models with differential equations. So technically, this should have been in the differential equation unit, but I decided to take this out and not include this until we talked about our BC topics. So we'll do that today. Tomorrow, I may or may not be out, so I wanted to flip-flop Tuesdays and Wednesdays, so that even if I'm here tomorrow, I think we'll still just go through the quiz review packet. So and then we'll save the arc length and distance travel. This is an easy topic. You're just taking the integral of a formula. So I think this is the easiest of all these topics here. So we'll do that on Wednesday instead. So tomorrow, regardless of whether I'm here or not, you guys will be working on pages 1 through 4 in your review worksheet number 1. Page 5 is the arc length, travel, and distance traveled. So pages 1 through 4 should all be topics that that we're familiar with in terms of what we've covered in class already. And so you guys just picked up the packet. There's 3. I put 3 quiz review packets and 3 quiz worksheets in there, review worksheets, and you guys also picked up the solution key. Tomorrow you'll just work on that. And basically reviewing everything that we've covered up till today. And then we'll have quite a few days to do quiz review. I may, after these days of review, I may go ahead and start a little bit on 9.1 on the 21st, but I will have morning reviews 21st and 22nd, going over any questions. And then if you feel like you've gone through all these reviews and you still want additional practice, then I would suggest that you go through the problems from your textbook, and those will give you some additional good practices as well. Okay. And the keys are all on the website for all the textbook problems. Okay. Right. And you will get to use your calculator on the quiz, but for certain problems, I'll be asking you for all the steps. Okay. Any questions about tomorrow? Okay, let's go to page 20. So logistic population growth is when the growth rate increases quickly at first. So we see a steep slope initially, but then it slows down as the population reaches its carrying capacity. So the graph will look something like this. Have you guys copy down a few things here? So here, your growth rate is initially going to be increasing. At some point, it's going to hit an inflection point, and that is going to be where the maximum steepness is going to occur. Your max growth rate is going to occur. It's going to occur at some time, and that time is going to be where your carrying capacity or your limiting value, half of your limiting value. So wherever your L is, L divided by 2 is where that point is going to occur. But then after that inflection point, your population is still growing, but then the growth rate is decreasing. See the steepness, the slope is kind of gradually leveling off. So for these logistic models, your population is continually increasing, but the growth rate is changing. A real world application could be with animals and how many animals the land can support. So, due to the limits of natural resources, the population is not going to continue to rise without bound, right? There's going to be some maximum that the land can support. Okay. So derivative of a logistic function is typically written in one of the following forms. dy dt equals k times y, parentheses 1 minus y over L. So this dependent variable y shows up twice in the differential equation, which indicates the likelihood of a logistic form. So if you ever see your dependent variable show up twice, either y is being squared or you see two different expressions with y's in it, that's an indication that, okay, they're probably trying to get us to make a match or to think in terms of a logistic differential equation. Or if we manipulate this algebraically, we could also get it to a form of k over L times y multiplied by L minus y. In either case, k and L are positive constants and L is your limiting value. So depending on the problem form, sometimes it's easier to make a match with this form, and sometimes it's easier to make a match with this form. And today we're just going to kind of look at these differential equations and kind of pull out the specific information that the problem is asking for. Let me write down those formulas again. We can reference them in our examples. Now, K is just going to be some constant that we may or may not have to involve in when we identify values. So let's read the directions here. Identify the limiting value and the y value of the point of inflection for each solution of the given differential equation. So if we look at number 1 here, dy dt equals 6y times 1 minus y over 3. This matches nicely with this first form, right? So what's my limiting value here? 3, yeah. So this matches nicely. There's some of the problems that we're going to see later requires us to maybe do a little bit of manipulation to pull, but this is matching very nice with the form that we have. The point of inflection is going to occur when it's L over 2. So the point of inflection is going to occur at the limiting value divided by 2. So when is that point of inflection going to occur then? 3 over 2, yeah. Because of L over 2. Number 2, dy dt equals 2y times 16 minus y. This matches nicely with the second form. What do you think our limiting value here is? 16, yeah. Now, there's a 16 that's hiding within the 2y, but it's hard to pull out because the k and the L are influencing what we see with that L there. So L is a lot better to pull from inside that parentheses instead of trying to pick it out from, because the 2 includes both the k and the L merged together. Okay. What's the y value of our point of inflection? 8, yeah. All right, so these two things will answer most questions you will see on the AP exam for logistics. The maximum value of the logistic function is limiting value, so being able to pull that L value is important. And the maximum rate, L over 2, those are the most common things that could be asked of you on the AP exam. But we're going to see some other variations within our notes. Okay, next page. Try 3 and 4 and see if you can pull those values just like how we did with 1 and 2. So number 3, our carrying capacity is that denominator that we see under y, so 100. And the maximum rate of a population is going to occur when y is equal to 50. Carrying capacity for number 4 is 7. maximum rate occurs at 7/2. Now, if we wanted to solve this differential equation, we would separate the variables, y is on the left, everything else on the right. If we took the antiderivative, it'll end up looking like this. Y is equal to L over 1 plus BE to the negative KT. This is the logistic form of a standard function. We're likely not going to see anything that is in this form, but just know that there is a solution of the derivative, but we're largely going to just remain in this form. We're largely not going to have to solve it, just have to be able to pull certain information at that differential equation level. Okay, let's look at number 5. The rate of change, dp over dt, of the number of people entering a state park is modeled by a logistic differential equation. The carrying capacity of a state park is 2,500 people. At a certain time, the number of people in the state park is 1,200 and is increasing at a rate of 100 people per hour. Create a differential equation that can represent this situation. So let's just use this equation here. Okay, so what information do we know? L, yeah. So L is 2,500. And then Y is going to be population P, right? So I'm going to just update my equation. And involve the variables that is referenced in this problem. Also, we know that at a certain time, the number of people in the park is 1,200 and increasing at a rate of 100 people per hour. So what can we assign to be 1,200? P, okay. At a rate of 100 people per hour. Yeah. And if we plug all that in, we should be able to solve for K. If we can solve for K, we can update this differential equation. So if you're cleaning up, you may be going down a different road of reducing, but we should all arrive at the same answer for K. So we're going to just update our equation and leave our dp over dt and the p variables alone, but the L and the K gets replaced. Yeah, any of these variations are fine as long as all of our L and our K gets replaced. Any variation of this is acceptable. All right, number 6, find the carrying capacity. If we can get it into one of our recognizable logistic equation or differential equation forms, we can find that L value, right? So let me just, what if we can just factor out the 4/5 y? See what that takes us. So factoring out something that is in the denominator, same thing as dividing. So if I did 150 divided by 4/5, sorry, 150 times 4/5. I get 120. If I double check, I should be able to get that 150 show up again. If I did 4/5 times 1 over 120, I'll get 1 over 150. So this is equivalent, but we want it in this form so that we can pull the L value a little bit easier. What's our L value? 20. Practice problems. A population of y changes at a rate modeled by the logistic differential equation dy dt, where t is measured in years. What are the values of y for which the population is increasing at a decreasing rate? So we're seeing indication of a rate of a rate. So we have to involve finding what? We have to find another derivative level down, right? Just that first derivative is not enough. It's asking, there's information about concavity here, right? Or the second derivative. So we're going to make our way down to our second derivative. Let me clean this up a little bit so I can just rely on power rule. I'm going to distribute that 0.3y through. Now, if I want to find the derivative here, this is with respect to time here. So d2y over dt2. It's a little bit of related rates feel because we're finding the derivative with respect to our independent variable time. So 1200y turns into what? Y becomes dy dt, yeah. Okay. I want to basically want to find my slope sine line for my y prime and my y double prime. So I can factor out that dy dt.
What? 6.
Oh yeah, sorry, you're right, 0.6y. So for dy dt is basically this, right? So we have 3 critical points. One is at 0, the other is at 4,000, and then the other is whatever causes this to be 0, 1200 minus 0.6y. So my critical points are 0, 4,000, and 2,000. If I want to test each subinterval here, I can test, let's say, 1,000. If I plug in 1,000, dy dt will be positive times positive, but then 1,200 minus 0.6y, or 0.6 times 1,000 is still also going to be positive as well. So positive for this subinterval. If I plug in 3,000, this will give me negative, but then these are still positive, so there's only one negative. Now, y prime, the only critical points are 0 and 4,000. If I plug in any value between 0 and 4,000, I'm going to get a positive number. So increasing, that means my y prime is always positive, so it's always increasing, but at a decreasing rate. So we want where y double prime is negative. So we're looking for this subinterval, right? Okay, we're going to skip example 2 and look at some of these multiple choices from page 23 on. Okay, take a look at number 3. The population P of a city at time t is increasing according to a logistic differential equation. Which of the following could be a differential equation? So we're trying to find one that matches one of the forms that we see. All right, so which one of these looks most like a logistic differential equation? Yeah, the last one, right? We know we're looking for 2 dependent variables here. Now, if you're looking at part B, this is not quite it, because dp over dt that t is now an independent variable. We want a dependent variable here. We want something that is involving the variable up top. So either y or in this case p is going to be the best fit. Yeah. All right, number 4, total positive number of positive COVID cases in the CDT days after the start of an outbreak is modeled by the function y equals c of t. And that is a solution to the differential equation given. If there are 10 reported positive COVID cases initially, what is the limiting value for the total number of positive cases of the COVID virus as t increases? You see the L value here. What's the limiting value? Yeah, 1600, right? And if you're thinking, wait, what happens with that 10? The 10 is just some starting value. We're looking for where the cases is going to cap off, so it doesn't really matter where we start. The limiting value is going to be the same regardless of whether we start at 10 or 5 or 0. Okay, the size of a rabbit population is modeled by the function r. That is a solution to the logistic differential equation, dr for dt, where t is measured in years, where t is greater than or equal to 0, and the initial population satisfies r of 0 equals greater than 0. Which of the following statements could be true? The limit as t approaches 0 of r of t is greater than 1,000. The graph of r has a point of inflection for t greater than 0. And the maximum rate of change of r occurs at t equals 0. So why don't we get our equation into one of the forms that we can more easily identify the parts. So I can factor out a 1/3 r from each term. So our graph may look something like this. We know our limiting value is at 800, so we know that 1 is definitely out. The graph of r has a point of inflection for t greater than 0. That's possible. But it's also possible that the maximum rate of change of r occurs at t equals 0. Maybe the graph looks something like this. We just know that the limiting value is 800. We don't know when that maximum is going to occur. So both of these options are possible. Okay, number 6. The rate of change dp over dt of the number of people in the mall is modeled by logistic differential equation. The maximum number of people allowed in the mall is 2,000. At 10 a.m., the number of people in the mall is 200 and is increasing at a rate of 400 people per hour. So what can we assign 2,000 to be? No. The number of people in the mall is 200. That could be what? P. So when P equals 200, the rate is increasing at 400 people per hour. What can we assign 400 to be? Yeah, EP over P. So we can use this to solve for K. If we can solve for K, then so let's plug in and see if we can solve for K and find a suitable solution here. So I'm just plugging in and solving for K. 400 in for dP over dt. L gets replaced with 2,000. Just cleaning up, K equals 20 over 9. And if I can update my dP over dt with my K value, that's going to match answer choice C. Number 7, the population P of a deer is jointly proportional to the size of the deer population and the difference between the deer population and the carrying capacity. So it's basically just describing one of the forms that we have available, right? Jointly proportional just means that we have two different variables being multiplied. There's a P multiplied with another P. So we have the size of the deer population, that's our P, and the difference between the deer population and the carrying capacity. So that's the L minus P. So basically just describing that differential equation that we've been working on. So we can replace L with 3,000. So we can get it into this form, but we can also multiply the 1/3,000 or distribute that 3,000 through and make it match one of our answer choices. So we just have to, be aware of both forms and just, whatever form we get, we can also just make it match whatever answer choice form that they have. Okay, let's try one more, number 8. Replace L with 5,000, replace P with 1,000, replace dP over dt with 500. Solve for K. Once you solve for K, then put it back into your dP over dt equation and make a match with answer choice C. Okay, your homework is to do the Euler's method problems that we did on we worked on Friday. But they all repeat. They're all basically the same process there. So let's just do the odds on page 18 to 19, and then page 50 to 52 are your AP practice problems. That's going to span Euler's method and L'Hopital's rule. I'll send out a reminder this afternoon of what your homework is, and these problems are also what a solution you can find on my website. And then tomorrow in class, we'll be working on pages 1 through 4 from our quiz review. Right, Mr. Krutz?
Can I send you the homework on this tonight?
Yeah.
Okay. Thank you.
Thanks.
5 more. I got 5 more.
Okay. Okay. How about you? Thank you.
I started like one. Wasn't it? Didn't you feel like that? You put it.
I don't think today it's done.
Yeah.
I'm gonna leave.
Oh, thanks.
Yep.
Thank you. During our work session. No. And.
The other half of Vaughn's notes and then
Thank you. I'm gonna go to an old teacher, Miss O'Brien.
Do you want one at least? No, I'm busy. Okay. I don't know. It's like kind of English, because he's not able to get the phone. I finished my equal. Oh, yeah.